Welcome to the deep dive. Today, we're tackling something really mind-bending from physics. Get this. Scientists have actually observed light behaving in a way they're describing with, well, imaginary time.
Yeah, it sounds pretty wild, doesn't it? Straight out of science fiction almost.
Exactly. But the fascinating part is that it seems to reveal something very, very real about physical processes. So our mission today is really to unpack that. How can something so abstract, imaginary numbers, right? How can they describe a real measurable thing happening with light?
That's the core question.
What does it even mean for light to experience imaginary time? And, how on earth could anyone actually see that happening? Let's dig in. Okay, so maybe we should start with the basics. Light. We're talking the whole spectrum, right? Radio waves, X-rays, visible light.
The entire electromagnetic spectrum, yes. And the key thing, the fundamental behavior we need to grasp, is that light travels. It propagates.
Right, it moves from point A to point B.
Exactly. But when it passes through stuff, transparent materials, for instance, its journey often gets, well, delayed.
Delayed. Okay. Is that a problem?
Oh, not at all.
Yeah.
Actually, it's incredibly useful. That delay tells physicists a huge amount about the material itself. You can sort of picture it like the light navigating these tiny atomic alleys and side streets within the material.
Huh. Atomic alleys, I like that.
Yeah. And technically, individual photons always zip along at the speed of light, c, but a whole pulse of light, a collection of waves, that can slow down or even seem to speed up sometimes because of how it interacts with the material. It's complex.
Okay, so interactions cause delays or apparent speed changes. And to describe this mathematically, physicists use imaginary numbers,
That's where it gets interesting, yeah.
which feels weird, right? Because imaginary numbers like the square root of -1, they're inherently abstract. They don't really map directly onto things we can, hold or count in the everyday world.
Precisely. They're mathematical constructs. But despite being abstract, they've been incredibly powerful tools in physics for a long time. Decades, really. They pop up in equations that describe all sorts of physical phenomena, and they've been especially vital for calculating those light transmission time delays we were just talking about.
Okay, so they were useful tools.
Very useful. But here's the thing. The specific physical behaviors that these imaginary numbers were actually accounting for in those calculations, that hadn't really been systematically pinned down or fully understood in experiments?
Ah, so the math worked, but the why from a physical perspective was a bit fuzzy.
Kinda, yeah. We knew they were necessary for the equations to match reality, but what physical process did that imaginary part truly represent? That was the missing piece. Until this new experiment.
Right, the new experiment. This was at the University of Maryland.
That's right, by Isabella Giovanelli and Stephen Allage. They designed a really elegant setup.
What did it involve? Was it incredibly complex?
Actually, no. Surprisingly simple in concept. They used basically a pair of coaxial cables, like the ones used for cable TV, essentially connected in a loop.
A loop of cable.
Yeah, forming what they call a ring graph, a simple circular path. And they sent pulses of microwave radiation through it.
Microwave, so still light, just not visible light.
Exactly. Same fundamental physics. And the key was they also used these cutting-edge oscilloscopes, really sensitive ones, capable of detecting incredibly tiny shifts in the frequency of the microwaves.
Ah, okay, so sensitive measurement was key.
Absolutely. This setup let them systematically probe that, previously theoretical role of imaginary numbers to see if there was a concrete, measurable physical effect tied to them.
So they're sending microwave pulses around this cable loop, measuring tiny frequency shifts. What did they find? What did tinkering with the pulses actually reveal about this imaginary part?
Okay, so this is the core discovery. They found that the imaginary numbers in the calculations weren't just some, mathematical quirk or describing some bizarre microwave daydream.
Yeah.
Instead, they precisely described a tiny but very real and measurable shift in the frequency of the microwave carrier wave.
A frequency shift.
Yes, a subtle change in the oscillation rate of the wave itself. And crucially, this shift happens as the pulse passes through the setup, and it's directly linked to how the transmitted pulse was being absorbed.
Absorption. Okay, so the imaginary part relates to how the material, or the setup in this case, absorbs some of the light's energy.
Exactly. Stephen Anlage put it really well. He said it was sort of like a hidden degree of freedom that people ignored.
A hidden degree of freedom.
Yeah, something that was always there, mathematically accounted for by the imaginary numbers, but not really recognized or measured as this specific physical effect, this frequency shift tied to absorption. He said they basically brought it out and given it a physical meaning.
That makes sense. So it wasn't truly hidden, maybe, but its physical reality wasn't appreciated or directly measured like this.
I think that's a good way to put it. The math told us something was happening, but this experiment isolates what that something is, this frequency shift due to absorption. And, this finding also helps clarify that slightly counterintuitive idea we mentioned earlier, how light pulses can sometimes seem to travel faster than individual photons.
How so?
Well, understanding this interplay between absorption and frequency shift gives us a more concrete mechanism to explain those apparent faster-than-light pulse speeds. It's about how the pulse reshapes as it travels and gets absorbed.
Got it. Okay, so this is really fascinating physics, but connecting it back to our listener, why is this significant? What's the so what here?
Well, the big takeaway, I think, is how this experiment really bridges the gap between abstract math and concrete reality. It shows that these imaginary numbers, which we might have just thought of as convenient mathematical tools, actually describe a real, tangible physical process.
So the math is the reality in a way.
In a very direct way, yes. It's describing this subtle frequency shift linked to absorption. It gives us a much deeper, clearer understanding of how light and matter interact, those photonic traffic conditions,
What are the atomic alleys?
Exactly. We now have a better map of what's happening in those alleys, specifically how energy loss or absorption affects the wave's frequency. And it's worth noting, this isn't just some fringe idea. The research has been accepted for publication in a top physics journal, Physical Review Letters. That's a significant stamp of validation.
Absolutely. So this deep dive really highlights something profound, doesn't it? That concepts we label imaginary in math can actually correspond to very real physical phenomena in our universe.
It challenges our notion of what imaginary even means in a physical context.
Which leads to a really interesting thought to leave folks with. If imaginary time, this mathematical construct, turns out to be physically linked to real things like frequency shifts and absorption, well, what other abstract concepts are lurking in our scientific theories?
Right. What other mathematical tools might just be waiting for the right experiment to reveal their concrete physical reality?
How many more of these hidden degrees of freedom are out there, shaping the world around us in ways we haven't fully grasped yet?
It certainly makes you wonder. There's still so much to discover.
Definitely something to keep exploring. Keep that curiosity going. Welcome to the deep dive. Today, we're tackling something really mind-bending from physics. Get this. Scientists have actually observed light behaving in a way they're describing with